Okay, I'm not sure I recorded the first part of the lecture, but it was just an introduction. So in the past, we were used to think that the water that is released downstream, not used, was wastewater, water that was wasted. Today, there is an increasing awareness of the fact that when you perturb the natural river regime, then you originate some environmental impact. The water that flows downstream is not wasted. It's water that goes into the recipient river, it's water that goes into the ocean, so it's not wasted. It's just following its natural cycle. And when you perturb the natural cycle, you originate some environmental impact, like, for instance, an impact on groundwater, because the replenishment of the groundwater reservoirs is impacted if you build artificial reservoir upstream. And also there are many concerns related to sediment transport, because when you build a new reservoir along a river, you trap the sediment, and therefore you originate downstream erosion processes, which facts have proved that are very much impacting. So there are many environmental concerns, and especially because the few locations left are affected by environmental problems like huge sediment transport, like reduced stability of the hill slopes over the reservoir. We don't want to repeat the disaster, the Bayonne disaster. And therefore, today, options for building a new reservoir are treated very carefully. But nevertheless, even if you already have a reservoir, it's becoming more and more urgent, the problem of revisiting the management strategies, because today we have new issues related to water, new requests, new situations. And therefore, the classical problem is, on one hand, the decision to build or not to build a reservoir. On the other hand, if you already have a reservoir, another classical problem is to find the optimal management strategy for the reservoir. In order to solve this problem, first of all, as I mentioned at the beginning of this course, of these classes, you have to collect any related information to the problem, which means any information related to societal development, any information related to water requests, any information related to industrial development that is foreseen for the future, any information related to agricultural development. So the situation of agriculture, how agriculture is evolving in the future, what is the most likely future scenario. So you have to collect any information related to society and water demands. Because on one hand you have to define the requests by also looking at the future. You have to elaborate a vision. On the other hand, you have to collect the hydrological information. So let's divide the water resources management problem, as I mentioned at the beginning, in the societal part and the hydrological part. Usually you may seek help for the societal part, while we have dealt with the hydrological part. And basically, the hydrological part means that you have to collect river flow data. If you have enough river flow data, then you can test your strategies by using the available data. This is almost always not the case, and therefore, depending on the problem, you have to decide what is the most advisable method to generate synthetic data. So if it's a non-intermittent river, you may, for instance, decide to use an autoregressive process. If you think that this approach is doable, and if you really see that the autoregressive process is providing a good fit. Otherwise, you may consider the opportunity of using RAIF for runoff models. But let's establish an important concept. If you want to make a vision for the future, if you want to elaborate a water resources management strategy for the future, basing on your on your expected time span of your planning, you have to collect a lot of data. A couple of years are not enough. If you want to test a strategy, you need to generate synthetic data in order to cover a long time span. And a rule of thumb, a basic rule, is that if you plan for 10 years, then you need at least 10 years of data. If you don't have them, you have to generate. If you plan for 50 years, you need to get 50 years of data. And if you don't have this river flow data, you have to generate them. Okay, now, let's suppose that our problem is to find an optimal strategy for managing the reservoir, which means how much water should I release during time? Because basically the reservoir stores water. Your decision is how much water to release. And of course you release water when you need to release it, meaning that you have requests downstream. If you want people to be able to take the water, you have to release it. And another possible use could be hydropower generation, and therefore you may decide to release water when you need to generate hydropower, basing on the information that you collected, and basing on your data set that you generated, you have to find the optimal decision. Now, the question is how to find this optimal decision. So again, we assume that we already have the reservoir. We don't take into account so far the decision whether or not to build it, but let's focus on the most frequent problem, even today, of finding the optimal management strategy. There is a possible approach that you may follow. Let's suppose that you generate 100 years of synthetic data. One possible approach is to work on expected values of river flow into the reservoir, because we have to generate the river flow into the reservoir. This is our synthetic series. This is our synthetic series, river flow into the reservoir. One possible approach, if you have a lot of years of data, is to focus on the expected values, the mean values of river flow into the reservoir during the year. Please note one important thing. When I say that I need to generate synthetic data into the reservoir, this means that the generation model, either a rainfall-runoff model or a stochastic process, must be calibrated with the same type of data, river flows into the reservoir. Which means that you don't have to collect the data downstream to calibrate the generation model. You have to look upstream, or you have to look at your inflow data. Many reservoirs, many managers, reservoir managers, they collect inflow data into the reservoir because they are useful for future planning. They know that these data are useful for future planning. But this is the type of data that you need to calibrate, to fit, and to generate. Okay, so I said a first possible approach is to study an average year. So to analyze a year that occurs, a hypothetical year, hydrological year that occurs on average. Therefore, this means that let's focus on daily data. From time step 1 to 365, you compute the average inflow in each day of the year. And if you generated 100 years of data, this means that this average is computed over 100 observations. You have 100 observations referred to the 1st of January and you compute the mean, 100 observations related to the 2nd of January and you compute the mean, and so forth. It's like computing a seasonal component. We already dealt with the problem of seasonal component estimation. This is a very similar problem. So you compute a representative inflow corresponding to an average year. Please note, we are in the presence of uncertainty here because the years are all different each other. So when I work on the average, I'm working on values that are affected by uncertainty. Any computation of the average is affected by uncertainty. And this is to be taken into account. We are using the approach of working with the averages. Note that this is a useful option if you don't foresee variations in the future from year to year. If you work on a representative year, you are implicitly assuming that your water resources management policy is applied in the same way over the whole period. Therefore, if I'm planning for 10 years, I'm trying to identify an amount of release from the reservoir that applies to the first year until the 10th. You have no variations, of course, because if you work on a representative year, you implicitly assume that you don't have changes along the lifespan of your management policy. If you have changes, you have to adopt a different option, and we will see. Okay, so how can we easily identify a management strategy by referring to the average year? First of all, what we should build here, sorry I forgot to indicate here that I'm representing the river flow. A useful graph is obtained by integrating this average hydrograph. And if I integrate this average hydrograph over time, I obtain a graph of the cumulative volume of water entering the reservoir. So I'm getting something like this. And let's indicate the volume with the symbol WT. Please note that the slope of this integral curve is equal to the river flow. If you take the derivative with respect to time of the inflowing volume, you obtain the river flow, because this second graph was obtained by integrating the first. So if you take the derivative of the second, you get back to the first. And the derivative is the slope of this curve. And therefore, when I drew this second graph, I tried to take into account the regime that is represented here. So I started with a low slope, and then here you have an increase of the slope because you have a first high flow period, and then you have summer where the slope is almost zero, but not zero because I'm assuming that some water is still entering, and then I have the fall with a second increase of the slope, and then at the end of the year the slope goes back to its initial value. You see that I took care of equating the slopes at the end and beginning of the integral curve. It's very important that you're able to read these graphs because they are a good opportunity to get a visual perspective and therefore an easy to get perspective on the river regime. And please note that this integral graph is a non-decreasing curve. This is non-decreasing because the volume, the inflow volume in the reservoir cannot decrease. The inflow volume can just increase. It can remain constant if you don't have any water entering, but when we are talking about inflow volume, of course, it can't be negative. This second graph that I drew here is very much helpful to understand possible strategies for releasing water from the reservoir. This is water that I am accumulating into the reservoir, and the graph of this accumulating water is very much helpful to identify possible strategies for releasing water. And another important feature of the reservoir is the storage capacity. Because of course, if the reservoir is huge, you have the capability of storing a lot of water. If the reservoir is small, of course, the regulation power of the reservoir is limited. So let's identify with W star the capacity of the reservoir. And please note that the capacity of the reservoir in principle is not a constant a long time, because it typically decreases a long time. Decreases because of siltation of the reservoir, which means it's accumulation of inflowing sediments. And if this reduction of the storage capacity is very much significant, you can't use this approach anymore, because you have a change a long time that doesn't allow you to refer to an average year. You have to use another approach. So let's assume a second assumption that the storage capacity W star is constant. Then let's indicate on this graph the storage capacity W star. And let's depict here a second curve, which is just the translation of this inflowing volume curve, and the amount of the translation is W star. So let me draw a second curve, which is just translated with respect to the first of the amount W star. The distance, the vertical distance between these two curves is constant and equal to W star. Now, let's suppose that at the beginning of the average year, so at day 1, you have some water stored in the reservoir. The reservoir is not empty. This is a general situation. If you can assume that the reservoir is empty. Generally, it is not, because at the beginning of the year, generally, you are at the end of an high flow season, and typically you have water in the reservoir. And let's indicate the amount W1 of water at the beginning of the year on this graph, and let's indicate it here, but starting from W star downward. So this is W1. So let's identify then this point here that I identified by indicating W1 starting from W start downward. This means that if you start from this point here, the reservoir is empty. If you start from here, the reservoir is full. Because of course W1 can vary between 0, reservoir empty, to W star, reservoir full. So this point here corresponds to empty reservoir. This point here corresponds to full reservoir. Now, let's suppose, let's remember what we have to do, not suppose, let's remember what we have to do. We have to define a management strategy for the reservoir, which means that we have to identify the amount of water that we can or won't release during the year. Therefore, we have defined day by day a QT, which would be not indicated as Q prime, which is the release from the reservoir. And of course, we can also identify a W prime T, which is the amount of water, the volume of water released from the reservoir. And let's start this integral curve of W1, let's draw it here, starting from this point. This is our 0 for W1. So we start from the point corresponding to W1 that we have identified, and let's draw from here the curve related to the cumulative volume released, W1. This is our 0 for W1. And let me state this basic principle. If I draw with a dashed line the curve corresponding to the amount of released volume W1, any curve that is inside these two continuous lines that I previously drawn is fine. Therefore, this could be one possibility. This could be one possibility, for instance, but any possibility that is included here is fine. And now let's try to understand why. First of all, let's identify some guidelines for our reasoning. Anytime that you intersect the lower curve, the reservoir is full, and anytime that you intersect the upper curve, the reservoir is empty. And let's try to understand why. For instance, let's concentrate on this first point here. I said that here the reservoir is full. Let's try to check if this is true. Let me draw a vertical line from here. And by drawing a vertical line, I have identified a segment which is the inflow volume from the beginning of the year. Okay, this is of course the inflow volume, because if I look at the lower curve, I see that this segment, which I can, no, I don't have colored chalks. This segment is the inflow volume from the beginning of the year. But at the same time, if I draw an horizontal line from this point, which is the starting point of the cumulative release, I notice that this is the release from the beginning of the year. And therefore, this segment here, which is left, is accumulation of water in the reservoir from the beginning of the year. Accumulation from beginning. Is it clear the concept? This longer segment that covers this span here is inflow accumulation from the beginning of the year. This shorter upper segment, it's outflow from the beginning of the year, this segment here, because I said that I'm starting to draw my outflow volume from my zero, which is here, and therefore this upper segment is my outflow. The difference between inflow and outflow is this continuous thick line, which is accumulation from the beginning of the year. But if I remember that at the beginning of the year I had this amount of stored volume, if I add to the volume that was stored at the beginning of the year this shorter segment, which is the volume accumulated from the beginning of the year, you see that I obtain a quantity that is equal to W star, which is the reservoir capacity. Therefore, it is proved that in this point here, I have the reservoir that is full. Is it clear? Or should I zoom? Should I explode the graph? With a similar reasoning, you can prove that when you intersect the upper curve, the reservoir is empty. And what happens when you collide against a curve like the lower one? Okay, the reservoir is full. If the reservoir is full, you cannot accumulate any more water, and therefore all additional water that gets into the reservoir, you have to release it. So you have to move forward with a slope of the dashed line that in this point here is equal to the slope, is tangente to the slope of the inflowing volume. This is the reason why you see here I drew the tangente. I don't remember in English, I have an amnesia, I think it's tangent, but I'm not sure. You have to move forward with the same slope. And the same occurs if you collide against the upper line, which means that the reservoir is empty, and therefore your maximum release is, of course, you can move with a different slope when you collide with the upper line, because you can decide to stop your release. But given that typically when the reservoir is empty, you need to release a lot of water, because otherwise the reservoir wouldn't be empty, typically you move forward with a slope that is equal to that of the incoming volume, because you release all the incoming water. In this way, you can devise a strategy to make an optimal use of water. And as I said, any dashed line that is included in between these two continuous lines representing the inflowing volume is a possible management strategy. Typically, by knowing the demands, the downstream demands, then you start with a dashed line that tends to satisfy all the demands, and then if you collide at a certain point with the upper curve, then of course you have to reduce your releases, therefore not satisfying the demands. Okay, now let me draw another curve, just because this is too complicated at this stage. Let me draw another graph which is similar, on which I want to identify a possible management strategy. So again, this is T from 1 to 365, and this is W, depending on time. And let's suppose that we have this type of incoming curve. And now let me shrinken the region between the two curves. This is W star. And let's suppose that this is our W1. So what happens typically in our climates? What happens typically is that at the beginning of the year, we don't need to release much water. And therefore, typically, let's say that this is June. Typically, in spring, we get to a situation where the reservoir is full. And then, but we don't need really water downstream. Usually we start needing water in June, or let's say May, around here. This is typically the time period in which we start needing water. So what we do, if we get to the status of full reservoir here, is just to follow with the release the inflowing curve, because we don't need to release more water. So typically what we do is just to follow the inflowing curve. We have to, because we cannot accumulate more water. So we have to follow this curve. But at a certain point, we get to a situation in which we need to start using more water than what is available. And therefore, from here, typically, what we do is this. And typically we arrive at that period, which is around July, where the reservoir is possibly empty. And therefore we are forced to follow this curve and to release all the incoming water until we get to such a situation. This is just an hypothesis, but it is representative because it shows that we indeed get to both the condition of reservoir full and empty. And of course there are different options. You may decide here to release less water in order to save some water for the second part of the summer. And this kind of decision is to be taken by simply writing an objective function, which of course depends on the releases during the year. And therefore you identify your best option. Now, here there are two important remarks that we have to make. The first remark is this kind of approach, which is interesting.